Hey everybody, let's do this Gizmo's calorimetry lab. Calor means heat. Calorimetry means to measure heat. Where have you heard the word calorie before? Most of you have heard it from food. Of course, that's big C, which is kilocalorie. One you know from food. Calorie with a big C. We're dealing with little calories. It's in an insulated container, blah, 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 blah. One simulation pane. Select copper. Use the slider to set its mass to 200 grams. What's the final temperature of the copper? Let's check it out. It tells me to do 200 here, 30 degrees for the water. Copper is 200 grams of copper. And 200 grams of water, and we want the copper's temperature to be at 90 degrees Celsius, and it is. So then we go over here to the graph, we click play. We see the temperature of the copper drop, and the water rises a little bit. So it says, what's the final temperature? Final temperature is 34.96 degrees Celsius. How much did the temperature of the copper change? Let's check it out. So we have 34.96. We know we started at 90 degrees minus 34.96 equals 55.04 degrees Celsius. How much did the water change? Well, we started at 30 degrees Celsius and it went to 34.96 degrees Celsius. Actually, I'm messing that up. I need to do the final first. Always final first. 30. Oh. Which means I didn't do this one right. This one goes from 34 to 90. And what that gives us is a negative 55.04. We'll just say 55 degrees Celsius. Okay, negative means it lost heat. When the temperature drops, it's negative. This one's 34.6 minus 30.0 equals 4.96 degrees Celsius. And this one is positive, means it gained in temperature. Right. It says specific heat is described as a substance's resistance to temperature change. Which one is a higher specific heat? Well, what's more resistant to temperature change? Clearly, the water only went up 4 while the other one went down 55. So water has a greater specific heat because its temperature changed less. Even though they had the same mass, 208 grams of each, the water only went up 4 degrees while the other one changed 55 degrees. And sure enough, water has a higher specific heat. How do you think increasing the water's mass would affect the final temperature? I think the final temperature will be lower. How do you think the copper's mass would affect the final temperature? Decreasing the copper's mass. Well, if I decrease the copper's mass, I think it's going to add less heat to the system. So I think that the temperature, the final temperature, will also be lower. How do I think increasing or decreasing the copper's initial temperature would affect the final temperature? Well, I think if I increase the copper's temp, Cu, temp, that would be increase final temp, put capital T, and ampersand. If I decrease copper's temp, then I think that will be a decrease in the TF, the final temperature. On here, they show us what we already did. and then we're going to make some changes and see what the final temperature is. So let's try that. So I've set up the parameters for the first blank space, and it said 90. The copper is the same as before, but we've changed the water to 2,000 grams. Let's run it and see what happens to the graph. And our final temperature this time is 30.54. Next, it says we're going to keep the water at 200, and we're going to change the copper to 20 grams and run that one. And our final temperature is also 30.54. Interesting. And then it says we're going to do two different ones. This one, we've increased the initial temperature of the copper. Let's see how it affects it. Compared to the initial 34.96, it raised it to 35.79 degrees Celsius. And conversely, if we lower the temperature and start at 50, what happens? We wind up with 31.65 degrees Celsius. And I've put the information into the thing, and I'm sure it's going to ask me to see if my predictions were right. And sure enough, what was the effect of increasing the water's mass? It was a lower final temperature. What was the effect of decreasing the copper's mass? It was also a lower final temperature. What was the effect of changing the initial temperature? Higher Ti of the copper led to a higher final temperature. It's an H in there. And then lower, sorry about my handwriting, lower T initial, T1 or Ti of the copper led to a lower Ti, which is, so my predictions were solid. How does changing the initial mass of the amount of the water's temperature increases depends on the mass of the water and the amount of energy of the copper. How does changing the initial mass of the copper affect how much heat energy it has? Well, less mass leads to less heat energy, Q. How does changing the initial temperature of the copper affect how much heat energy it has? Well, less initial temperature leads to less Q. And conversely, more mass of the initial copper at the same temperature is more heat. More initial temperature of the same mass means more heat. Q, quantity of heat. Many gyms and health clubs have steam saunas, which are small steam-filled rooms. Traditionally, steam saunas have a container of heated rocks. A small ladle of water is poured on the rocks in order to make them steam. Use what you have learned so far about heat transfer to explain how the rocks can be used to make steam. Well, when you pour the water on the rocks, heat energy is transferred to the H2O, and it boils and becomes steam, which is H2O gas. So we go from H2O liquid, H2OL, and it boils to H2O gas. Water becomes steam. Why do you think only a small ladle full of water is poured on the rocks at one time? Because H2O has a high specific heat too much water wouldn't boil. It wouldn't raise the temperature enough. Might even cool down the rocks more than we want them to. So you want just a little bit. Okay, the next one says, how do you think you can use the calorimeter to compare the specific heat capacities of the substances listed on the gizmo? Well, if we're looking at the gizmo, we're going to test different substances, and we're going to keep the temperature the same, the mass the same on the substance and on the water, and we're going to see how does it change the final temperature. The ones that have the higher final temperature are going to have higher specific heat capacities because they're more resistant to change. They should wind up with a higher temperature because they're, of course, starting higher. They shouldn't drop as much. Let's try it. First, we got to fill in this part. We're going to test different substances, and we're going to make sure we're going to keep all the temperatures and masses the same, and the independent variable, the different substances will be the independent variable. Keeping the temperature and the mass the same will be a constant variable. Which substance do you think will have the highest specific heat capacity? Well, our dependent variable, the substance that, for lack of a better word, leaves the highest TF, final temperature, will have the highest heat capacity. Now, I think it's going to be ice. Why? Because ice is the same as water. As far as the substance, it's H2O. It's just in a solid form. I'm predicting that ice will have the highest. Because water has such a high heat capacity, I think ice will also even have maybe even a higher heat capacity. And how do we write heat capacity? We write with little c. Specific heat, little c. Next part says we're going to set these up and see what the final temperature is. We're going to notice that all the parameters are the same for the different substances. And we're not testing ice yet, but let's see. Between granite and lead, I think granite will have the most heat resistance, the highest specific heat capacity, because I don't know, I'm guessing because granite's not all metal. Like these guys are metal. I mean, I think this will be lower than copper, but I think granite will be the I think lead's final temperature will be higher than copper because I think copper's a better conductor of heat, but I think granite's the worst conductor of heat, so it's going to be the highest final temperature. I really don't know. I'm going to test it. So let's set it up. We're going to have granite. We're going to have, let's see, it says start at 90 degrees, 200 grams, yes. 30 degrees, 200 grams. Okay, so let's test granite. We're going to push play and see what the final temperature is. Oh, I don't think I like my prediction. Let's see. No? Oh, yeah, 39.59. It was higher. Writing that down. And let's test the lead. 90 degrees, 200 grams, 30 degrees, 200 grams. We're going to test just lead. We got to get granite out of there. Just lead. And here we go. Wow, lead was the lowest. Lead is the best conductor of heat and electricity. You know what? I should have known that because they do use lead. You can use lead to conduct electricity. The lead from your the lead in your pencil is actually graphite, so that doesn't really count. But I guess lead is a really good conductor. I'm learning. So I've written down my final temperatures. Of the three substances, which caused the largest temperature change in the water? What does this indicate about the relative specific heat? The largest temperature change was lead. Lead, Pb, had the largest temperature change. How do we write temperature change? Delta T. So it has the highest little c, specific heat. Okay, interpret. Remember that specific heat capacity is a measure of a substance's resistance to temperature change. Oh wait, I did this wrong. Wait a minute, hold on a second. It doesn't have the highest, it was the most willing to change, has the largest temperature change. Lead went from all the way at 90 degrees all the way down to 31.75. So it is the least resistance to change. So it is the lowest specific heat capacity. Ooh, I almost blew it. Remember that specific heat capacity is a measure of the substance's resistance to temperature change. The more resistant a substance is to temperature change, the higher its specific heat. Rank 3 substances in order of their specific heat capacities. Highest to lowest. Well, the most resistant was granite. So that was the highest heat capacity, most resistant to change. The next one was copper, or Cu, right? And the next one is lead, or Pb. It goes in that order. The next step says, how do you think the specific heat capacity of ice will compare to that of copper? I think it's going to be the highest. Will have the highest, I already said this earlier, heat capacity. So let's test it. It says deselect lead and select ice. Use the default temps -30, 50. Set the water temperature to 60 and the water mass to 200. And we're going to have to do some math to compare the two, I think. Let's check it out. Let's do these parameters first. It says deselect lead, select ice. It says set the ice to -30 and 50. These are default, meaning they automatically should be there, but it says to set the water temperature to 60 and have 200 grams, which we do. Click play. And you can see that the ice disappeared. Why? Because it's going to melt, right? So let's answer the questions. What was the final temperature? What was the final temperature? Final temperature was 28.83 degrees Celsius down here. What do you think is happening when the ice line on the graph is at 0 for a long period of time? Why do you think the line disappears after that? Well, what's happening for the ice is that, let's go back to that. So this ice, it's first the energy is going into raising the temperature. Here, when it gets to 0, which is the melting point of ice, the energy is going into turning ice into water, or turning solid into liquid, and that's called the latent heat of fusion. It's unfusing the molecules of water. So if we go to our answer sheet, what do I think is happening? At 0 degrees Celsius, it flattens because it's at its melting point. It is at its, so apostrophe here, no apostrophe here. Okay. Why does the line disappear? Because the ice is now water. And if we look at that graph, well, this blue line is water. This ice is now just joining the water now that they've reached the same temperature. All right, it's just joining the water. It's all melted, and it just is now at the same temperature as the water, this final T. Question says, how much water temperature did the water experience? How much temperature change? Well, it's always TF minus TI. So the final temperature was 28.83 degrees Celsius minus the initial temperature of 60 degrees Celsius equals, can I do that in my head? Ow, my head hurts. 1.17 plus another 30. So 31.17 degrees Celsius. Negative. It lost temperature. Negative 31.17. Next part says, how does this change in water's temperature compare to the change caused by other substances you tested? Well, this changed 30 degrees. If we look here, the water temperature here changed 4 degrees. It changed 9 degrees. It changed 1.75 with way more substance to change it. Here we only had 50 grams of ice, and it changed it way more. Why? Because that ice is way more resistant to change. So the water temperature changed way more. So ice clearly has a very high specific heat. Next part says we're going to try to test the heat to melt something for a phase change. Remember, phase change is melting, boiling, or condensing, or freezing. So we're going to click reset. We're going to set the temperature to negative. We're going to do these parameters. Let's do it now. To select ice, it says to make the temperature of the ice to be negative 100. It says to make the mass 50 grams. We have that. Set the water temperature to 50 degrees Celsius. And the mass 200 grams. We have that. And so now we're going to click play. And it says, what's our final temperature? And our final temperature was 13.39 degrees Celsius. Do you think the ice all melted? Well, I see that it disappeared here, so I think it did. Yes, because the light blue line that represents ice, right? This light blue line represents ice, disappeared. Okay, it says look at the graph. The graph shows two separate stages. It says the heating of the ice and then the melting of the ice. How much did the water's temperature change while the ice was melting? How much did it change while the ice was heating? How much did it change while the ice was melting? Oh, that's a good question. Let's check it out. So if I'm looking at here, the water changed pretty rapidly while it was heating, and then it kind of flattened out while it was heating. So here it didn't really do much. And then when it started melting, it dropped again, really dropped more. So it went initial heating, and then melting, and then it flattened out again. Pretty cool. So what was the temperature change? While it was heating, it went from 50 down to the halfway between 25 and 50, which is, what is that, 37.5 or something like 30? Yeah. So it dropped about 12.5. Then while it was melting, it went from 37.5 all the way down to 7.5. That's a 30-degree drop, if I'm not mistaken. So it dropped way more while it was melting. You can even see from here to here is one increment. From here to here is 2 increments, almost twice as much of a drop. So it dropped more while it was melting. Let's write that down. The temperature changed more while the temperature of the water, that is, TH2O you could write, changed more while the ice was melting than when it was heating. Heating. How does this experiment demonstrate ice's specific heat capacity? Good question. We definitely know that ice has a relatively high heat capacity because it doesn't want to change much. And then when it's melting, it has something called the latent heat of fusion, which is the energy to melt the ice. But we won't get into that. Let's just leave it at that. It's fine. Activity C gets us into this equation. Q equals MC delta T, where Q is the energy used to heat something, or the energy it loses as it cools. And this is M is the mass, C is the specific heat capacity, and the change in temperature is delta T. So you can read this. It's measured in joules. The specific heat is joules per grams degrees Celsius. That's little c. Temperature is in degrees Celsius. And Q will be in joules. This Q will come out in joules. And mass, of course, is in grams. So let's try it. When you mix two substances, the heat gained by one substance is equal to the heat lost by the other. Suppose you place 125 grams of aluminum in a calorimeter with 1,000 grams of water. The water changes temperature by 2 degrees and the aluminum changes by negative 74.95. So A is asking use a specific heat capacity equation right here to find out how much energy the water gained. So we're going to say Q, which is energy, equals mc delta T. The mass of the water is what we want, which is right here, 1,000 grams of water. The C, it tells us right here, is the specific heat of water, 4.184 joules per gram degree Celsius. And the change in temperature is 2 degrees. It says that water changes by 2 degrees, so I put 2 degrees Celsius in here. I cancel out my units, degrees Celsius, grams and grams, and I'm left with joules, which is how we measure heat, so we're in good shape. And we just multiply all these together, and we get our answer. We say 1,000 times 4.184 times 2, and we get 8,368 joules, or 8.368 kilojoules. All right. And then the next part says, assume that the heat energy gained by the water is equal to the heat energy lost by the aluminum. That makes sense. And use a specific heat equation to solve for the specific heat of aluminum. Well, if the energy is the same for aluminum, and we know that Q equals mc delta T, the energy that it lost will be equal to this number. However, it's going to be the negative because whatever this gained, the other one's losing. But we're trying to solve for C, so divide both sides by m delta T, and we get little c equals Q over m delta T. So we're just going to plug in. We know that the Q is 8,368 joules, but the negative version because it lost as much energy as water gained. And then the mass of the aluminum up here was 125 grams. And the temperature change of the aluminum said that it changed by negative 74.95 degrees Celsius. And so these negatives are going to cancel each other out. And I get 8,368 negative divided by 125 divided by 74.95 negative, and I get a 0.893 joules per gram degree Celsius, which is our unit for heat capacity. And so we're in good shape. Then it says aluminum's accepted specific heat is 0.90. Use this value to check your work. Oh, looks pretty close to me. All righty. Sorry, I see now that it was cut off, so here's the answers. So it says use the gizmo to mix 200 grams of copper at 100 degrees Celsius with 1,000 grams of water at 20 degrees Celsius. What's the final temperature? Let's do it. Parameters it asks for. We got 100 degrees Celsius, copper, 200, massive 200. Oh, looks like I left the ice in there. I got to get that out of there. Let's try that again. 100, 200, 20, 1,000. And we're in business. Let's play it. There's our graph, and it says record the final temperature, which we see is 21.42 degrees Celsius. Calculate the temperature change of each substance by subtracting the initial from the final. I totally disagree. It's final. Oh, yeah, from the final. Yeah, so final minus initial. Let's do that. So what's our initial of the water? Our initial temperature was 20 degrees Celsius. Uh-oh. Final minus initial. Final minus initial. TF minus TI. Our final was 21.42 degrees Celsius for both of them. Right? They found this. They had the same final temperature. For water, I'm going to subtract its initial, which is 20.0 degrees Celsius. And I'm going to get 1.42 degrees Celsius. And for this one, I'm going to subtract its initial temperature, which was 100 degrees Celsius. And I'm going to do it on my calculator because I don't feel like figuring that out in my head. And we're going to get a negative 78.58 degrees Celsius because it lost energy. That's our answer here. Okay, I jumped ahead a little bit, and it says how much heat energy did the water gain? We know our formula is Q mc delta T. We have our M for water and our delta T. And up here is our specific heat of water. So we're going to plug those in. 1,000 grams of water times 4.184 joules per grams degrees Celsius times the delta T for water, which was 1.42 degrees Celsius. Degrees Celsius cancels out, grams cancel out. I'm left with joules. I put that into my calculator, and I see that 1,000 times 4.184 times 1.42 equals 5,941 joules for water. That's the first part. The next part says, now solve for the specific heat of copper. Well, we already figured out how to get specific heat. We isolated specific heat up here. So we have Q over M delta T. We know our Q is going to be the opposite of the water gain. The energy gained by the water is going to be what was lost by the copper. So I'm going to say negative 5,941 joules over the mass, which is 200 grams of copper, and the delta T, which was negative 78.58 degrees Celsius. I'm going to cancel out the negatives because I don't feel like putting them in my calculator. If you have a negative on the top and the bottom, they go away. Got 5,941 divided by 200 divided by 78.58, and you get a solid 0.378 joules per gram degrees Celsius. I wonder if that's a reasonable answer. What's the specific? Let me ask Siri here. What's the specific heat of copper? Let's see what Siri would be so kind. And Siri's saying that it's 0.3273. That sounds pretty close. I think we did pretty good. So that's our answer right here. All right, good job. Last page. It's almost over. What a bummer. Use the gizmo to mix 200 grams of granite at 100 degrees with 1,000 grams of water at 20 degrees. What's the final temperature? Let's do it. Okay, I got it all set up according to what they asked me to do. Now I'm going to check the graph and see the final temperature. And it looks like the final temperature is going to be 22.93 degrees Celsius. And we're going to calculate the temperature change of each substance. Let's do it. Okay, so I did the final mass initial of both. I got 2.93 degrees Celsius for delta T here of negative 77.07. How much heat energy did the water gain? Again, Q equals mc delta T. We're going to plug in the mass, which was 1,000 grams. The 4.184 joules per gram degrees Celsius, always the specific heat of water. And the temperature change, which is 2.93 degrees Celsius. Plug that into our calculator. 1,226 joules. Now it says, now solve for the specific heat of granite. Oh, it's the same old thing. We know that C equals, what does it equal again? Q over M delta T. We know that the Q is the negative of what we gained from the water, negative 1,226 joules. And the mass of the granite was 200 grams. And the delta T was negative 77.07. And we get 1,226 and divided by 200 divided by 77.07, and we get 0.0795 joules per grams degrees Celsius, a very low specific heat, which is what we expected. Repeat the steps with A through D with lead. All right, let's just see. See if Siri knows. What's the specific heat of granite? Do you know, Siri? Nope. Not so easy. Granite is a mixture. It's not a pure substance, so Siri's probably not going to be able to pop it out. But for lead, you can do it. I'm going to let you do the last one on your own. Okay, number 4. In calorimetry, the energy gained or lost by the water is going to be equal to the negative energy of whatever the substance we put in there. And of course, Q equals mc delta T. And this is MC delta T for the substance. This is for water. We'll just, everything over here is water and everything here is granite because the question's asking about granite. It says how many grams of granite, so it wants to know the M of granite is our unknown. At initial temperature of 80 degrees Celsius must mix with 300 grams of water at 20 degrees Celsius, and they both go to 20.45. So we need to know the delta T over here, which is TF minus TI, and we need to know the delta T over here, which is TF minus TI of the granite. Now the TF is going to be the same for both, 20.45 degrees Celsius, 20.45 degrees Celsius, but the water starts at 20 degrees, and the granite starts at 80 degrees. So we're going to subtract, and this one's easy. I got 0.45 degrees Celsius. For this one, I get a delta T of a lot, almost 60, just under 60. So what's that? 59.55 degrees Celsius negative. Okay, what's our C for each? Our little C for water is always 4.184 joules per grams degrees Celsius. And we figured out earlier that C for granite is this, but I'm looking up here, I noticed I did something wrong because it said there's 1,000 grams of water and I only put 100. So that would move this over one. So our answer is actually for the specific heat because that moves this over. This is actually a more joules, and this becomes an extra 0 comes here, and so this becomes 0.795 joules per grams degree Celsius. So we're going to say 0.795 joules per grams degree Celsius. And now we have everything we need, and we're solving for, these are equal to each other, right? Q is equal to Q, MC delta T. We're solving for the mass of the granite, which is here. So I want to solve for this. I want to divide both sides by C delta T of the granite. This is of the granite. So we don't forget, I'm going to make a little label. And then I'm just going to say mass equals M of the water, which is the 3,000 grams of water. The C of the water, which sounds funny, it's like a sea of water, is always 4.184 joules per grams degrees Celsius. And the delta T of water, we figured out, was 0.45 degrees Celsius over the specific heat of the granite, which we figured out up here is 0.795 joules per grams degrees Celsius, times the delta T of the granite, which was negative 59.55 degrees Celsius. And let's plug it into our trusty calculator. And we get 3,000 times 4.184 times 0.45 equals, divided by 0.795 divided by a negative 0.55 negative. And we get that it lost, well, is that possible? Where's our negative here? We should have a negative around here somewhere. We can't have a negative mass. What's the negative I'm missing here? Something went wrong. Let me pause. Okay, I see where we went wrong. Q equals negative Q, so this has to be negative. So we have a negative here. Just put it on the top. That's going to cancel out our negative here. That's why. Okay, so that leaves us mass of 119 grams of granite. Okay, so is that answer what we wanted? Let's see if check if our units cancel out. Grams, Celsius, joules on the top, joules on the bottom. Degrees Celsius here, degrees. Now we have grams on the bottom of the bottom, which makes grams go to the top, which is what we want. So we have 119 grams of granite. It says go to the simulation and see if this works. Everything we have, what we found, the mass we found, the initial temperature of granite they gave us, the initial temperature of water they gave us, and 3,000 grams of water they gave us. We put it inside our calorimeter, and we want to see if the final temperature comes out to what they said, 20.45. I'm nervous. I'm not going to lie to you. Let's see if it comes out to 20.45. Come on, granite. Hey now, look at that. All right, so story checks out according to our simulation. Nice. Okay, the very last part says a calorie is the amount of energy needed to change the temperature of 1 gram per 1 degree Celsius. So that's 1 calorie changes 1 gram, 1 degree Celsius. So there's 1 calorie per gram degree Celsius. We know that the specific heat of water, this is the to change the energy to change 1 gram of water. So this is 1 calorie. This is all for water. We know that the specific heat of water is 4.184 joules per gram degree Celsius. And so you can see that these are the same. If these cancel out, the 1 calorie equals 4.184 joules. Suppose a snack bar is burned in a calorimeter. Oh man, it's a waste of a perfectly good snack bar. Let's call it a Snickers because snack bar doesn't sound as appetizing. You know what? Let's call it a Kit Kat. I like those better. And heats 2,000 grams of water by 20 degrees. How much heat was released? Use the specific heat equation. Give your answer in both joules and calories. All right, that's easy. The energy in the snack bar is going to equal the energy absorbed by the water. So if Q equals mc delta T and the water changed by 20 degrees, that's our delta T, and 2,000 grams of water. And of course we know C for water. So we want joules and calories. Let's start with joules because we're good at that. We got 2,000 grams of water is with a 4.184 joules per grams degree Celsius. Specific heat is raised by 20 degrees Celsius. Well, let's put that in our calculator. And it would seem that our candy bar, our Kit Kat, holds 4.184 times 20 equals, oh, that's a lot of energy. That's 167,360 joules of energy in a candy bar. That's no wonder you don't want to eat too many of those. And so we know that we're going to multiply that. We know that there's 1 calorie for every 4.184 joules. So we just divide this by 4.184. Try that again. 167,360 divided by 4.184 equals, oh, it was right, 40,000 calories, which is the calories we talk about. That's 40 big C calories. That's 40 kilocalories. So when you talk calories in your food, you're actually it's 40 calories. So don't panic. How many kilocalories does a snack bar contain? 40 calories, 40 kilocalories. 40 big C calories that we call calories that are actually 40 kilocalories. So when you look at your food products and it says there's 40 calories, it's actually kilocalories, or cal with big C, as in Cal, as in Berkeley, as in Go Bears. Go Bears! Thanks, everybody.